And let's move on to Joakim Rosdahl, who's going to tell us about SPHINX.
Thank you, Ramil. Can you hear me?
Yep.
Excellent. Good morning, good afternoon, and good night. I'm Joakim. Thanks to the organizers for having me here. So I'm going to focus this talk on the escape fraction of ionizing radiation from simulated galaxies and real galaxies as well. So observationally, we only really know about the escape fraction at low redshift. We know it's very low at low redshift. We don't know very much observationally at redshift beyond about 3. Theoretically, we need the escape fraction to be high at high redshift because otherwise we can't reionize the universe. So theoretical models have come up with forms of the escape fraction as a function of time that look like this. They generally tend to increase with increasing redshift to conform to these observations and reionization. So it's hard to confirm this form of the escape fraction, and it's hard to explain. So my question is today: can we use simulations to verify this form of the escape fraction and to then try to understand why this happens? So for this, we use the SPHINX cosmological simulations. These are fully cosmological radiation hydrodynamical simulations containing about 25,000 star-forming galaxies at redshift 6. And the resolution is high enough that we can start to predict both the escape of ionizing radiation from individual galaxies without making assumptions, and the reionization history in the same simulation. So this mosaic is just supposed to give you a feeling for the kind of range of morphologies of galaxies that we have in those simulations. Just very quickly about the setup, we use the Ramsey's RT code, adaptive mesh refinement. We have volumes that are 10 and 20 co-moving megaparsec in width, physical resolution down to 10 parsec in the ISM of galaxies. We use a very bursty star formation, such that star formation efficiency locally can be very high, and that also leads to a very bursty feedback by supernova explosions. We include ionizing radiative transfer with the M1 method using the BPAS SCD model that gives us luminosities as a function of stellar radius and metallicities, and there is no calibration on unresolved escape fractions. So I just want to emphasize, this has actually been emphasized in a few talks already, that reionization is bursty and kind of flashy in those simulations. So here's an example of a galaxy, just one typical galaxy in SPHINX. You see the escape fractions in thick and ionizing luminosity in thin, which basically represents the star formation rate, which is very fluctuating. And the escape fraction kind of follows the fluctuations in star formation because the escape fraction is really regulated by feedback in those simulations. So I was tempted to show movies, but it's a bit dangerous on Zoom. So you can actually go to the Slack channel for this talk to see a couple of movies to see actually how the radiation is being flashed into the intergalactic medium in those simulations. Okay, so let's compare a bit to observations of the UV luminosity function at redshift 6. So the muted colors here show you observational data. The dashed curve is SPHINX intrinsic UV luminosities from the SPHINX galaxies. And if we take into account dust attenuation, we get a pretty good agreement with observations at all magnitudes that are included in the simulation. So this gives us a kind of good confidence that our galaxies are fairly realistic in their star formation rates. And the budget, more importantly, for reionization is more or less correct. We have the correct number of photons produced per volume in the simulation. Okay, so here is the reionization history in 3 variations of the SPHINX simulation. We're going to focus on this one, which is the largest volume that we have. It reionizes a bit late, even pushing the lateness that has been presented to us in previous talks in this conference. It's not too bad though. To show you the effect of volume size, you can see the yellow dotted curve. And you can also see the blue dotted curve, which shows you what happens if we switch just versions of the BPAS model. So you can see that subtle modifications in the SSP model, they actually have huge impact on the reionization in these simulations via the escape fractions. Okay, so here are the escape fractions then, just global average, luminosity weighted average escape fractions in two versions of the SPHINX simulation, so smaller volume and larger volume, both with the newest version of PPAS. And indeed, pretty much like expected from these theoretical models, the escape fraction starts out high and then it does decrease with redshift. Not as much as in these models, but definitely this is something which is happening in the simulation. So that's very exciting. It's a kind of a verification, and now we can hopefully use the simulations to try to understand what is driving this evolution and the decreasing escape fractions with time. So going to the literature, there have been a few theories over the years of why such a thing could happen. First, there is an evolution towards more massive galaxies with time, and if we assume that more massive galaxies have lower escape fractions, as Anne was mentioning before, this would lead to a global decrease in the escape fraction. In just the same way, there is an evolution towards more metal-rich galaxies, and if they have lower escape fractions, this will also lead to the same thing. There have also been suggestions that there is a lower kind of intensity of star formation in the universe with time. And if we assume again that escape fractions are driven by feedback from star formation, then this should also lead to a decrease in escape fractions with time. So let's investigate this in the SPHINX simulations. First of all, here is the sensitivity or variance with escape fractions to stellar mass of galaxies. So these are just bins of galaxies. Note that there's a huge scatter, but what you see here in blue is the mean escape fraction of galaxies given luminosity weighted mean escape fraction given a stellar mass. And you find that there is a distinct peak in the escape fraction at intermediate stellar masses of 10 to the 7 solar masses-ish. And if you go to higher galaxy masses, there is a drop in escape fractions to almost zero escape fraction at 10 to the 10 solar masses. So indeed, we predict, as many others have before, the escape fraction decreases with galaxy mass. You can see here in the red curve the cumulative intrinsic luminosity of galaxies below a given stellar mass. And then you can see in the purple curve just a convolution of the red and the blue. So basically an escaping luminosity below a given stellar mass. And you can see that the peak here and the drop in escape fraction, it shifts the escaping luminosity compared to the intrinsic one. Now for metallicity, there is a pretty much similar evolution. So at low metallicities, there is a relatively high escape fraction, and then with high metallicities approaching solar metallicity, it goes down to almost zero. So both factors, in a sense, could regulate an escape fraction that decreases with redshift. Given that there is an evolution towards higher metallicities and higher stellar mass. So now we look at the evolution of the escape fraction versus stellar mass versus galaxy mass with redshift. So this is just the same plot as I showed before. Before it was stacked overall redshifts, and now this is individual like redshift ranges. So now you see that the shape is pretty much always the same. There is always a peak around 10 to the 7 solar masses, but the magnitude is decreasing quite a bit with time. So for a given galaxy mass, the escape fraction decreases with time. So you can't then say that it's just the evolution towards more massive galaxies, which is regulating the escape fraction in this case. I'm not going to show it, but there's a very similar trend for metallicities. These also have the same shape, but decreasing magnitudes with time. So we can conclude from that neither the evolution towards more massive galaxies nor high metallicities is dominating the regulation in escape fractions decreasing with time. So now we can look at the intensity of star formation. We look at that in the form of the specific star formation rate. I'm going to say SSFR because it's a tongue twister. The specific star formation rate is just a star formation rate over the mass of the galaxy. And we look at the star formation rate over 10 million years, which means that the SSFR can be in the range 0 to 100 per gigayear. So now if you look at the evolution here of the specific star formation rate with redshift, we find that it does decrease with time. Okay. So good start. Then we plot the escape fraction versus the specific star formation rate of galaxies, again, across a range of redshifts. And first of all, there is a very distinct trend that galaxies with high specific star formation rates, they have the highest escape fractions. If you go to lower SSFRs, lower escape fractions. If you look at now the shape and the magnitude of this relation, it pretty much stays constant over all redshifts, which does really indicate now that what's regulating the decrease in escape fractions is just the shift of this red curve here from being dominant at high specific star formation rates at high redshifts to being dominated by galaxies with low specific or relatively low specific star formation rates at low redshift. So to drive that a bit further home, we can try to isolate galaxies with specific star formation rates and see if they retain a constant escape fraction. If they do, then that's a very clear indication that the evolution in escape fraction is just dominated by galaxies shifting towards lower and lower specific star formation rates. Okay, so here is the global escape fraction for all the galaxies in the SPHINX volume. So now we take the galaxies with the highest specific star formation rates. These are enormous specific star formation rates. And if we only take those galaxies, they indeed do have a pretty much constant escape fraction over time. If you look at the shaded region, you find that the relative amount of ionizing luminosity being emitted by these galaxies is decreasing with time. Then if you take the next spin in specific star formation rates, you again find a roughly constant escape fraction. And you see here how the luminosity is dominated by these galaxies. And we can continue. And then it becomes kind of obvious that the escape fraction is kind of constant for all classes of galaxies. But there is just a shift from the luminosity being dominated by high specific star formation rates to low specific star formation rates at low redshifts. So the evolution in escape fraction is there. And it is regulated by this decreasingly intense star formation in the universe. So that's all I wanted to say. I will just leave you with a summary here. I've done exactly 10 minutes, so I'm done. Thank you.
All right, thank you very much. That was really interesting stuff, amazing simulations. So yeah, we have some questions already on the chat.
So one question is, in the Bursty star formation example, why is there a delay between UV luminosity and F escape for the second group of star formation events, but not for the first group, whether it's local density?
Whoa, that was a loaded question. Can you repeat that?
In the Bursty star formation example, why is there a delay between UV luminosity and F escape for the second group of star formation events, but not for the first group?
I guess this is a reference to the plot here.
Yeah.
For an individual galaxy, it's a bit, things are very chaotic here, and nothing is kind of perfect. There is never a perfect trend between, sometimes you can have an intense episode of star formation, which is not followed by a high escape fraction. And even, possibly vice versa, things are kind of merging, and there are accretion events. There's all kinds of stuff that complicates things. So I guess that's my answer, if I understood the question correctly.
Okay, if you're not, you can just answer that on Slack.
Absolutely. Yeah.
Another question is, in your model, to which UV luminosity do M star of 10 to the 7 galaxies roughly correspond?
10 to the 10. So
10 to the 7.
10 to the 7.
10 to the 7.
So the peak.
Yep.
I think it's around minus 17, but I have to come back to that. So I have looked at it. I don't have the plot in this bunch of slides, but I think it's around minus 17.
And over what time scale is specific star formation rate averaged? Do you explore time delays, i.e., does F escaping galaxies lack specific star formation rate bursts?
Yeah, so actually, there's a subtle point that I didn't really have time to discuss here. We look at specific star formation rates over 10 million years, indeed. As you can see here, we are also looking at maximum specific star formation rates over the last 100 million years. So if you only take galaxies that currently have high specific star formation rates, you don't get the same very nice trend. And that's because galaxies that have recently had high specific star formation rates, they tend to, if they have been very high, they tend to kind of blow up. And they go to very low specific star formation rates, but high escape fractions. and they can remain luminous for a few million years, maybe 20 million years, something like that. So therefore, it's important to look at recent high specific star formation rates rather than current ones.